Welcome everyone to the new technology stream. I'm very pleased to have Paul Gartman and Ben Hicks, who are going to give us a presentation on zOS containers and the container platform. So thank you, gentlemen, for putting this together. A bit of admin, the session is being recorded, which means obviously that you can see it again and listen to it again if you want, and obviously pass it on to your colleagues. Once it's up on the GSE website, which hopefully will be soon after the event is finished. Please stay on mute. If you want to ask a question, obviously unmute and ask the question, but please then go back onto mute so we can cut out all the background noise. I haven't got much more to say, so over to Paul and Ben. Thank you very much.
Good morning, good afternoon, and good evening, everybody. I'm Paul Gartman, and today with Ben Hicks, we'll be taking you through configuring the zOS container platform. For our agenda today, we're going to start off with a quick high-level overview of containers and Kubernetes. And then we'll get into what the zOS container platform is and how it fits into the broader picture of IBM's container offerings. Then we'll touch on the base setup, getting you set up for Podman. And then I'll hand it off to Ben, and he'll walk you through the setup for your Kubernetes cluster, getting your first zOS control plane appliance set up, and then set up for your worker nodes in order to run your application traffic. For the overview of containers and Kubernetes, we're going to assume that you're familiar with container technology and Kubernetes already. So I'll just be giving a quicker, higher level overview here. A container is a standard unit which combines your application with all of its required dependencies. So if you have a Python-based application, you would have your Python application as well as all of its requisite dependencies, those whether that's Python 3 or OpenSSL or things like that. It'll all be packaged and shipped as one combined unit. What these containers do is they provide an isolated running environment that's highly portable and lightweight. This lets you rapidly scale up or down and be a lot more reactive as opposed to a virtual machine. And the reason for its lightweightness is because it utilizes the underlying operating system. So as opposed to having the full copy of the operating system in every image, like a virtual machine, it's much smaller and more lightweight. Because of this, though, containers are architecture and operating specific. Now, the overall trend of application development has been to break your large monolithic applications into many smaller microservices. So instead of one giant block, which handles your logging in, your data capture, your checkout, your database management, now you would split all of those into their own service, which can be scaled as needed. And that's where microservices come into play. Microservices are perfect for containers. They're built for purpose. But if you're making all of these containers, it's probably difficult to manage I just mentioned 6 different types of containers, and they're probably each going to have large numbers of containers running for that purpose. That's where Kubernetes comes into play. Kubernetes is the orchestration platform which allows you and makes it much easier to manage these containers. It'll let you do things like automated rollout. It'll monitor the state of the cluster, give you healing capabilities if containers come down. There's a lot of other features there, but at a high level, it makes your life easier for managing containers. From an architecture perspective, Kubernetes has control plane nodes and worker nodes. The control plane node is what's actually providing the infrastructure for the Kubernetes cluster, and the worker node is what's running your actual application traffic. That's what's running your microservices. You can think of the control plane as your brain and the worker node as your body. The control plane node you can see is a lot busier. It has many different containers that are all running a purpose for that Kubernetes cluster. For example, the kube scheduler, which will handle the scheduling and picking what node containers will be going on, whereas the worker node is a little bit quieter. It just has the utilities and daemons as well as the runtime present on it because that's focused on running your actual traffic. Now, how does zOS Container Platform fit into the broader picture? Well, IBM already has a container offering for Linux. Those would be running your Linux S390X images. As I mentioned, containers are architecture and operating system specific. And if you had your Linux containers before, you could run them on either natively on Linux with Linux on IBM Z, or you could run them on zOS in a Linux address space, which is running on zOS through ZCX or ZCX Foundation for Red Hat OpenShift, where Red Hat OpenShift is the orchestration for large numbers of containers for ZCX. Now, this gave you the ability to run your Linux containers either natively on Linux or on zOS. But what zOS Container Platform does is that provides you the ability to actually run zOS containers. So this would be zOS S390X containers that are running natively on zOS. And this is providing it with an industry standard container experience. Now, in order to accomplish that experience, there are a lot of components that had to either be ported from the open source world, from the Linux world, or had to be created in order to support this. The first of these utilities are Scopio and Podman. Scopio is what's used for transferring images between registries. So if you're pulling your image from the IBM container registry into your private container registry, that's what you use Scopio for. Podman is what you'll then use that image that you pulled down. You'll build your own image on top of that base image, and then you'll use Podman to do that build. You'll use Podman to run it, to test it. That's another standard utility from the open source world. And again, with these utilities, the experience is similar to that of on zOS. It's similar to how it works on Linux. Next, you have the container runtime. This is what's actually going to be handling the life cycle of the container. You have the CNI, which will handle all of the networking for that container. I'll touch more on that when we get into the networking setup. And then you have Conmon and runC, which are handling the creation and stopping, as well as the communication in the background for what's going into starting and stopping those containers. Now we'll touch on Kubernetes. Again, a large number of components here that had to be ported or created from the open source community. I forgot to mention the CNI is one of those components that we actually created ourselves. From the Kubernetes perspective, you have the kubelet. This is the agent for the node, which will work with the runtime and the scheduler and make those decisions about what's going to be running where. And that's one of the communication focal points. Then you have cryctl, which is a command line interface for cryo. Cryo being the runtime for Kubernetes, which works in conjunction with runC. Then you have kubectl. kubectl is your main hook into the Kubernetes cluster. This is what you'll use when you're creating resources, when you're creating services, when you're deploying your actual traffic. Now, I've mentioned some components that we had to create. kubeadmz and CAM are components that we created ourselves in order to work with the zOS control plane appliance and the Kubernetes control plane node. For some background, if we had wanted to get a Kubernetes control plane node to run natively on zOS, it would have meant porting almost the entire Linux kernel. So instead, what we did was we created an appliance, which is a Linux address space running inside zOS, whose built for purpose is to just run a Kubernetes control plane node. Then we provided kubeadmz and CAM for working with that control plane appliance. So kubeadmz is the tool that you'll use to initialize the Kubernetes control plane node, to join a control plane appliance into an existing cluster. And CAM is the tool that you use more for debug, for gathering log information from that control plane appliance address. Now, from a file system perspective, this looks a little bit different than typical. This is because there's an overt upgrade action that will need to be performed. The open source community is shipping every 3 or 4 months, and we're going to be matching that. And so we'll need to support multiple versions or have multiple versions in order to give customers time to go through the upgrade. Part of that as well is that Kubernetes only has a SKU policy of one version. So if you have a 129 cluster, you can't go straight to 132. You have to go sequentially from 129 to 130 and so on and so forth. And because of that, the ZFS layout and the PDSE layout looks a little bit different, having these versions that you can upgrade to get to the latest version. Now for the base setup to run and build your containers using Podman, we provide a zOSMF workflow, which will walk you through the setup process in order to get containers set up on each system where you would like containers to run. This workflow should be ran on every system that you want containers to be running on. You can see the name of the workflow there. The expectation is that the user that's running the workflow will be either UID 0 or have access to BPX Superuser. And this is a guided experience, so every workflow step will make clear exactly what the requirements are and what it will be doing. There's also some supporting scripts to help automate some of these steps. So some of them are automated, some of them are manual. A manual step example will be a security setup. We probably don't want that running automatically, and therefore your security administrator will be the one performing that step. You can see on the right what this looks like as an example of when you create the workflow, all of the steps that we'll be walking through today. Now, starting off at the top, for zOS Container Platform support, there were several new kinds of file systems that have to be created and added in order for containers to work. And so the first workflow step is validating that your BPX ParmLab member has these file system types enabled. Those three being the union file system, the temporary file system, and the proc file system. The union file system provides a merged view of two or more directories. So you'll have a higher level directory, which is read and write, and then you'll have one or more lower level directories, which are read only. This is used extensively by containers as a way of saving space. If you have 100 container images that are, 100 containers all running the same image, there's a significant amount of that storage that is common amongst all 100 container images, and therefore that they can all share that base layer and have their own write space on top of that. Another performance improvement is the temporary file system. This is an in-memory physical file system that's not written out to DASD. Containers, Podman and Cryo both make extensive use of temporary file systems for maintaining state of containers, and therefore this is a performance improvement for not having to constantly take I/O to write out to DASD. From a proc file system perspective, this is more of a Linux concept, which is a pseudo file system, which represents the current state of the system and all of the processes that are running on top of it. Again, this is another thing that containers require, and therefore that support has to be, or that file system has to be enabled for containers. The next workflow step handles adding the path, updating your path to include these new ZFSs that I showed previously. And this will just give you access to those binaries. With all of these, you'll need to update either your Etsy profile or your Etsy RC in order for these to persist across IPLs or your BPX ParmLab member. There's an appendix at the end which contains what a sample BPX ParmLab member would look like as well. Now, one of those manual steps I talked about is for the manual security step for Podman. This is a step that will be ran by the zOS security administrator. We provide a sample job of what that JCL will look like. And this JCL will walk you through creating a Podman group that provides access to the containers Unix privilege class to those non-UID 0 users, which are in this group. And it also contains the connect command in order to add those users to the group. Now, why is running as non-UID 0 important? Well, Podman, when you're running a pod, those pods will run under the user ID of the user that submitted it. So if you're running as root, your containers will be running as root. You probably don't want your containers to run as root. And furthermore, if your users have to be root in order to run containers, you'll either have a lot of root users or not a lot of users that can run containers, which is also not ideal. Podman provides rootless Podman support. There's no difference between the commands itself, between if you're running as rootless or if you're running as root. It's just the underlying user, which is running those actual commands. On the right, I have a reference slide, which, shows some of the differences in the configuration between a root user and a rootless user, and some of the differences in where those configuration files are coming from. Now, there is still a requirement for pulling some images that a user is an administrator. This is because some of those images have require APF authorization, and therefore you'll still need to be root for pulling some of those images. The next steps will walk you through the file system setup, the first of which is the permanent file system setup. So you can see on the right what that looks like from the workflow step, as well as filling in some of the default values with the primary size and secondary size, as well as the name. If you're SMS managed or not, you can also see some of those variables depending on how your shop is set up. You can, you can specify those there. This permanent file system setup will hold all of the persistent storage for container images or other persistent artifacts that those containers create. It will be mounted on varlib podman by default, and it will create the varlib podman storage directory for those root users. Now, if you're rootless, the next workflow step will handle the sharing of that podman file system to those non-UID0 users. What that step will do is it will create var share container storage as a bind mount to varlib podman storage, such that those non-UID0 users have access to run those container images. After that, you'll be setting up the temporary file systems, those being var run containers, var run runc, and var run user. All of these will store the various metadata, the first two for UID0 users, and the third one for non-UID0 users. So we've created all of those file systems. Now we need to populate them with configuration information. So the next workflow step will copy the default config files into the Etsy containers directory, assuming they don't already exist. Again, this is very similar to Podman on other platforms. So if you're familiar with both the configuration files themselves and how they work and some of the values you can specify, functions very similarly. The containers conf contains the default configuration options for Podman, and the mounts conf contains the default mounts, which will be which will be bind mounted when you run a container. Storage conf specifies the container storage options, and you can see on the right an example of what that looks like, as well as some of the differences I was talking about earlier between the rootless users and the root users in terms of where that data is being stored. Next, you have the registry conf. This is what determines what image registries Podman will pull from. For example, ICR, the IBM Container Registry, is enabled by default. This is also where you can block specific registries or namespaces. All of this is just the surface level of customization with defaults. There's a plethora of options which you can go through to configure these. Next, there's a policy.json, which this determines whether an image should be accepted according to either signature validation or things like that. The default here is to deny all images. And so that will be something that you'll need to take a specific action on in order to allow images to be pulled from based on a signature validation or something like that. Next, for the networking setup, this is one of the areas where we differ from the Linux community. So in Linux, they provide the network isolation through private networking. However, if we were going to be doing that, again, it would have required porting the Linux kernel. And on zOS, we already have a concept of dynamic VIPA technology, which can be used to provide this network isolation and also leverage all of the benefits that the VIPA technology provides. So instead, we've created our own CNI plugins, which will leverage these Viper ranges. Before I get into that, I just want to mention real quick that if you're in a common INET environment running multiple stacks, you'll need to set stack affinity. This is not, being common INET is not something that we recommend. It's legacy support, but if you are running it, you will need to do that. Now, what a CNI does is this is the specification which defines how containers are added to, removed from the networking. So a CNI plugin will implement the CNI specification. That CNI plugin will be invoked by Podman or Cryo, and then that CNI plugin will handle allocating the IP addresses or returning the IP addresses, supporting the life cycle of those pods. Now, those pods and containers use ephemeral IP addresses. And so when an IP address, when a pod comes up, it's given an IP address. And when it comes down, it gives that back to the range. When it comes back up, it will have a random IP address again that may or may not be the same. The CNI supports both IPv4 and IPv6. However, it defaults to use IPv4, and it can only be IPv4 or IPv6. It cannot be both. Kubernetes is recommended to be IPv4. However, Podman can be one or the other. Now, this workflow step will create the zOS CNI configuration file that I mentioned here below. And that configuration file is what will define where those plugins are located, as well as if you're using IPv4 or IPv6. Now, from a devipa perspective, you'll need to define a zcontainer Viper range. I've attached a sample here, and which defines the 10.10.21 range. And you can see the subnet mask there and the IP address. And that zcontainer range is where those pod IP addresses will be allocated from. Next, for WLM setup, this is another area where you're probably going to want to take an overt action. By default, the zOS container platform work, if you don't do anything, will be classified as sysother. This is a very low priority and is likely not something that you'll want. You'll probably want to be higher than sysother. At a high level, if you want all of your container traffic to be categorized the same, there's the syscontainer service class that's created. This provides a default value for all of your container traffic for both Podman and Kubernetes. That's probably at a minimum of what you'll want to do and specify that higher than sysother. But there's also container qualifiers which can be used if you want a higher level of granularity for setting up your WM traffic for certain containers and pods. After we've gone through all of this, we've provided an initial verification program, which will build and run a hello world container image to validate that all of your file systems are set up, that everything's mounted and enabled as you would expect, and that all the install directories are in place, that LE's been updated, and things like that. You can see the cutout of what it's doing. It's checking that the proc file system's mounted, that the UFS and TFS are there, that the bin directory is there, and then it's going to start building the container image. I want to call out that this is building it from scratch. That's important because you won't have to have set up your registry access at this point yet. This is going to be building a local Rex image from a local, there's no network connectivity needed to go out and get a repository image. And you can see that the IVP ran successfully. You're probably not going to want, you're going to want your now container images that you can build on top of. And that's where the IBM Cloud Container Registry comes into play. These container images that IBM provides are only going to be shipped to ICR. You're entitled to these with your zOS license. The credentials are provided in an image entitlement memo on ShopZ. The list of container images is constantly growing that IBM provides. But to call out a few, we provide a base zOS image, a Java 8, Java 17 image, a zOS Connect image, a Go image, Node, Python. That list is constantly updating. And those are the base images that you'll be using to build your applications on top of. You would use Scopio to copy these from ICR down to your local registries that you can access in your shop. I mentioned earlier that you'll have to update your policy.json in order to accept these images. You can see here I attached what the default looks like with the type reject. This will, by default, reject all images. And so I've attached, again, a sample command, which you can use to accept images from ICR. And then you can pull them down and use them locally. You'll probably want a private container registry. What this will allow you to do is to build and run your custom container images within your organization and hosting them internally. This also means that every system which is running containers won't need access to ICR. Instead, you could have your private container registry, and then your local systems would interface with that private container registry. We've attached a blog post which will walk you through configuring a private container registry using ZCX. Those are all the steps that you'll go through setting up Podman. And now I'll hand it off to Ben to walk you through setting up a Kubernetes cluster.
Thanks, Paul. So yeah, I'll walk through what is needed to do the Kubernetes cluster portion and how to set up a cluster environment. So to start, I want to kind of give a diagram of what a cluster looks like on zOS CP, since there are some differences from Linux that Paul kind of mentioned briefly already. So here we have two zOS systems, and each zOS system is a worker node. Just like on Linux, you can only have one worker node per system. Then we have our zOS control plane appliances, or ZCPAs. These, like Paul had mentioned, contain a single control plane node within them, and that's the only purpose of them. However, because the node is contained within the appliance, you're able to run multiple ZCPAs on one system, and you can run a ZCPA on the same system as a worker node, which is unlike Linux, where you can only have one node per system. Then we have our pods as well. And in order to enable high availability support, we have Syspex distributor support, which enables distribution to the ZCPAs. And this is so that no external systems are needed outside of zOS. And also, in order to have high availability, we recommend having at least 3 ZCPAs so that if any one goes down, you still have a cluster. Now, we did lock down the ZCPAs, so you cannot SSH into them, and there's no scheduling abilities like you might see on a standard control plane node. So Paul had gone over the new command line interface tools that we made because of that. We have kubeadmz, which is made for the Kubernetes administrators. This helps you manage the lifecycle of the cluster, while CAM is for the system programmers, and this manages the lifecycle of the ZCPA. So now we need to go and set this up. So what we're going to be walking through now is first how to set up the ZCPAs, and then how to set up the worker nodes. So let's start with the ZCPA. Just like with the base zOSCP setup for Podman, we have a zOSMF workflow that we need to run through. This workflow will provision a single ZCPA at the latest version that you have installed on your system. So that means you have to run this once for every single ZCPA you want. So if you have a high availability environment, you need to run this 3 times. What this does is it creates both a ZFS instance directory, which contains config and startup information for the ZCPA, and a collection of vSAM datasets that contain the Linux file system, which contains the control plane node. In step 1 here, this is where we need to gather all of the information. This includes stuff like the ZCPA name, the high-level qualifier for the vSAM datasets, the instance directory, and your storage type if you're using vol seers or SMS storage classes. You also need to specify a group here so that other users other than the one running this workflow are able to access the ZCPA. And there is a security setup required in step 1. This is required once on each system that you want to be able to run kubeadmz and cam commands. So if you only need to run kubeadmz and cam commands on one system, then you only need to do the security setup one time, and you can skip it for the rest of the work. The rest of the times you run through the workflow. Once you do step 1, steps 2 through 4 are all automatic, and they will go ahead and create and fill the instance directory and the data sets. Then step 5, you can go in and it will give you a command to start the ZCPA that you just created. And then step 6 will give you a mount command so you can mount it after a re-IPL. Now, as Paul mentioned, these are set in WLM as sysother by default. So we recommend classifying them as high priority so that they're a crucial part of the cluster. There is some networking setup as well here. This is within the step 1 gather step that we just went over. We need to put a IPv4 address here that is assigned to the ZCPA. Similar to the zcontainer stuff, this is defined in our TCP/IP profile using a Viper range defined ZCPA statement. Notice though, this Viper range statement has a mask of one IP address. So we are defining a Viper here of a singular IP, in this case 10.10.10.1. You'll need to define one of these Viper ranges for every single ZCPA that you create. Then if you have a high availability environment and you want sysplex distributor support, then you will put that IP address here as well. This is defined also in the TCP/IP profile using the Viper distribute xtarg statement, where the keyword xtarg specifies that this distributor is distributing to ZCPAs. Notice that we do not support IPv6 within the ZCPA. So even though our pods do support IPv6, we recommend keeping the entire cluster at IPv4 for simplicity. For the security setup, we need to be able to run kubeadmz and cam commands. So to start, there is a group called k8sadmin that once you create that group and give proper permissions to it, you can go ahead and add any user to that group, and those users will be able to then run kubeadmz commands. For cam, there's no group, so each user will have to be added individually, both by giving them access to the SAF resource, bcze.cam, and any required ICSF SAF profiles that are listed within the sample. Then we need to create a public-private key pair and connect it to a certificate in a keyring. This is in order for us to authenticate with the GCPA. And then finally, we have some operator commands in order to start and stop cryo and kubelet, which we'll be going over in a second, but there are two parts of the worker node that get started and stopped whenever we do a worker node join or a worker node reset using kubeadmz. And that's all for the GCPA setup. At that point, you will have 3 GCPAs provisioned on your system, and you are able to go ahead and run your kubeadmz commands to initialize and join them into a cluster. A few key differences with Kubernetes and Podman I should run through real quick. Kubernetes stores images in a different directory than Podman does, which means if you are building an image with Podman and you want to try and run it with Kubernetes, you cannot just run it. You will have to push it into a private registry and then pull the image back down with Kubernetes in order for Kubernetes to have access to it. Additionally, in Podman, the pods always run under the identity of the user. In this case, that does not have to be the case, and Kubernetes can change users. So what we recommend is that we create a generic user, which I'll be going over in the security setup in a few slides. And this generic user has minimal permissions so that there's no unauthorized access to containers, and containers have least permissions possible. So what we need to do now is set up the worker node. So the primary components of that are Cryo and Kubelet. Cryo is an implementation of the Kubernetes container runtime interface, and this is what actually allows the deployment of containers by calling runc. And then Kubelet is what communicates via a REST API with the control plane node to learn about any tasks that need to be taken. Just like with the other two parts, we have another workflow. This workflow you have to run once on every system that you want to be a worker node. So unlike the ZCPA, where you might need to run the ZCPA workflow twice on one system if you want two ZCPAs on that system, this one you need to just run once. Most of these steps are manual, but they will walk through what's needed, similar to the base zOSCP setup. And you will need UID 0 or access to BPX superuser. To start, what we want to do is copy the starter procedures, Cryo and Kubelet, into our proc lib. These, as I mentioned, if you created the operator commands properly in the last security setup we had, then these will be started and stopped automatically, which means you won't have to worry about any manual work after you do this initial setup. Once you rename them and copy them over, if you have a common INET environment, which we recommend against, but if you do, there is a step 0 we provide that you can uncomment and specify what stack name to run these under. Now we have a symbolic symbol we need to define as well, k-ver. This version, you want to point to whatever version you are currently running with. And Paul had kind of gone over this briefly about how we have some versioned PDSEs and version binaries in order to have an upgrade path. So that's this symbolic symbol will tell Cryo and Kubelet, as well as we define a path as well to define where to look for these binaries and executables at any given time. So in this case, this path would resolve to zOSCP/1.32/bin, and that's where we would look. And this symbolic symbol will need to be updated if you ever perform an upgrade and put it at whatever version you are currently at so that you have the right Cryo and Kubelet versions being run. Okay, now we have the security setup that we need to go through. Here's the generic user I mentioned before, OCI user. This will allow the containers to run with the minimal privileges necessary. And you can select a different user ID if you want, but we generally recommend against it because it's just more setup and more hassle that's required as the end user. Now, we want to give cryo read access to this surrogate class, bpx srv.oci user you see here, which I'll be going over why that is in just a second. So now we need to create two new user IDs as well, one for cryo and one for kubelet. They both need to be UID 0 in order to have proper permissions. Cryo also needs a few additional things. First is read access to this facility that's listed. This is because some container images have APF authorization, so this allows Cryo to run them. We also need read access to Unix priv containers, which allows the user to create namespaces. And then finally, we recommend defining bpx.daemon. And what this does is it will make it so that runc can only swap to IDs that have been explicitly permitted. So that surrogate class that we defined on the last page, that class comes into play here, where if we give Cryo read access to that, then runc will only be able to swap to OCI user when running a container. And all containers will be run as OCI user at this point. Now we have some file systems we want to create. For the permanent ones, similar to both CCPA and Podman, you can specify your volseers or SMS storage classes depending on what type of storage you use. And we have one temporary file system as well. This temporary one is there because we do not need to persist var run cryo after reIPL, since it only contains container file systems. For the permanent ones, the ones you might want to make a note of are var log cryo and var log kubelet. These contain the log files for cryo and kubelet, respectively. Additionally, etc Kubernetes contains the config files used by kubelet when joining as a worker node, so that might be helpful as well. And of course, especially for the temporary file system, you should add all of these into your VPX PRM farmland member. Now we want to populate them with some configuration files. These files are automatically created, and you likely won't need to make any changes here. If you do, though, the changes you might make would be at the very top, you see kubelet port. This port, if it's already used on your system, you would need to change that to a free port, obviously. And also, in the middle, there's a Kubernetes version. If this version is not what you are currently running with, then you'll need to change that as well. But this should be whatever your GCPA is running at. After these files are created, if you did change any default file locations or anything else earlier on in some of the setup process, then you will need to go into these files and edit them as needed to ensure they point to their correct locations. And that's it for all of the required setup for worker nodes. Now there's a couple of optional quality of life steps that we recommend. First is if you have syslogd configured and active on your system, then cryo and kubelet will print all of their log files to syslogd. So we recommend defining some lines in the syslogd configuration file so that cryo and kubelet will print to their own log files instead, and it will be easier to debug any issues you find. Of course, you'll have to give the K8s admin group read permissions to these files as well. And then finally, we have a version health check. This health check will print a console message when an upgrade is available on your system and has been installed. The other way to check this, if you don't want to add this check, is every time you start up a ZCPA, it will print this message you see on the right here. So if we look, we see the current appliance and available appliance. The current appliance says it's at 1.31, and the available one is at 1.32. So we know we have an upgrade available, and we can go ahead and perform an upgrade. Once we've done all of that, we're done with the workflows needed to create a Kubernetes cluster. So the next steps would be ahead and going to run kubeadmz commands to initialize and join the cluster, and then running kubectl commands to go ahead and deploy your pods as well. And that's all we had. Were there any questions?
Well, if not, thank you all very much for joining.
Yes, thank you all. Thank you, Paul and Ben. Very good presentation. This is a specialized area that my son works in, so I hear about it all the time, about containers. So I think it's going to take off up on the mainframe especially. I know it's everywhere else already. So thank you for taking the time out to present. As I say, this is being recorded so that people can reread it and or listen to it and give it to their colleagues. And if there's no other questions, I thank you all for your time, and I hope you have an enjoyable rest of the day. Thank you very much.